All right, this is lesson 1-2's homework assignment. We are on page 16. Starting with number 1 through 4, we're going to give 2 instances of each pattern. An instance is basically an example, so you can choose anything to plug in. So I'm going to start with the actual expression or equation that is considered the pattern here. So y minus y equals 0. 2 instances, 2 examples, plugging in something for y. Now, if you plug in something for y here, the same value has to get plugged in here. So let's say I choose 2 to go in for y equals 2. So it goes 2 minus 2 equals 0. So with 2, that pattern holds true. Let's try something else. Now, as we dig deeper into these instances, we want to test and try and find things that don't work. So let's try a negative number, because if a positive number works, most positive numbers will probably work. So let's try y equals negative 5. So if we do negative 5 minus negative 5 equals 0, minus the negative actually goes plus plus, and they will cancel each other and give you 0. So this pattern holds true and works. And so we're just proving that by providing examples or instances. So number 2, x plus x equals 2x. I'm going to start with x equals 1. So 1 plus 1 equals 2 times 1. Show that that's true. Now, actually, we don't have to solve this all the way out if we don't want to, because it just says give an instance. Okay, but you could solve this out and see that you're going to get 2 on this side, 2 on this side. This holds true. And so how about x equals 0? So 0 plus 0 equals 2 times 0. There's another instance. So for these instances, you don't even have to solve them all the way out, unless it specifically asks you to. Okay, we're just giving an example, plugging in. So number 3, x times x equals x squared. So let's do x equals 3. 3 times 3 equals 3 squared, and we know that's true. And let's put in a negative, so x equals negative 2. So negative 2 times negative 2 equals negative 2 squared, which is true. All right, and number 4, now we have multiple variables here, so we have to plug in for both of them. And so I'm going to go with x equals 1 and y equals 5. Just randomly pick numbers. Now, every x has to get the 1 and every y has to get the 5. So we got to plug that in correctly throughout the whole thing. So we're going to go 1 over 5 equals 1 times 1 over 5. And that would hold true. So how about x equals negative 2, y equals 4. So we're going to get negative 2 over 4 equals negative 2 times 1 over 4. And those would be equal. Okay, number 5 now. Kind of going backwards. This can be a little confusing in terms of the directions. What are they asking for? So if you look 1 through 4, it says give 2 instances of the pattern. So these are the patterns given with a variable. And you came up with the instance, which was kind of plugging in numbers. So in 5 and 6, you look, everything that you're given here is basically an instance. These are instances because it's all numbers. They want you to describe the pattern using one variable. So basically go backwards. So here we were given the variables, we plugged in numbers. Here the numbers are already plugged in. We're going backwards and plugging in variables. So the trick on these is to notice what is consistent throughout all of these, because those numbers won't change. So what I'm saying is that when I see this 3 constantly here, I know that's part of my pattern. So notice you can have a number in these. They're not all variables, right? Although most of them were. But if you notice the 9, the 4, the 90, they change. The 2's don't change. The 1's don't change. That's part of the pattern. But the 9, the 4, the 90, if you notice, it ends up in all 3 of these instances. So this is what's changing. A 9 got plugged in, a 4 got plugged in, a 90 got plugged in. The 3's are always there, the 2's are always there, the 1's are always there. Those are part of the pattern. So we need to keep that there. So we're describing this pattern with one variable. And so when I write this out, anything that stays constant stays. This next term, this next piece of this is what's changing. So I'm going to call that x. That's what something's being plugged in for. Minus 2. 2 is always there. Equals 1. 1 is always there. Plus, now whatever number got plugged in here also got plugged in here. So there's my x again. And number 6, same idea. Try and find the stuff that's staying the same, find the stuff that's changing. This first term is absolutely changing, so I'm going to call that x plus 2 plus 2 plus 2. That's part of the pattern, so I need the plus 2 times. Now here's my 15, it shows up again here. Here's my 1/3, it shows up again here. 47.1 shows up again here. So whatever was plugged in here also gets plugged in here. So that's x again. Equals, every single one of these starts with a 3. That is part of the pattern. And once again, here's 15, here's 1/3, here's 47.1. So that is x. All right, next up we had number 8. So a group consisting of 1 adult and 5 children went to a special kids baseball game. Special prices are shown here. Fill in the group's costs for each item. So starting with tickets, if you were going to show your work, we have 1 adult and 5 children. So we have 1 times 17 plus 5 times 10. And maybe you would have just wrote that out, 17 and 50, but you did the mental math, so show where it came from. So this is 17 plus 50. So the cost of the tickets here is $67. And this is part A. Let's see, hot dogs. So 1 adult, so 1 hot dog for $5. 5 children, 5, 4, 3, 50. If you get in the habit of writing it out like this, we're actually building up towards writing the expression, which is where most people struggle. I ask you, okay, write this in algebra with a variable representing the possible adults and children. Well, you're just plugging into these spots. These are your variables. These are the spots that we're plugging in here in the pattern, in the instance. So right here we have 5 plus, this comes out to 1750 for a total of 2250. And then the drinks. Adults are $3, so 1 $3 plus 5 $2. So obviously that's 3 plus 10 for a total of $13. So part B, now where everybody struggles, write the algebraic expression that would describe the group's cost for any item in terms of the adult price and the child's price with the little p. So the 1 was how many adults we have. So if we are going to start a new problem with any number of adults, that's going to be the p plus 5 times the lowercase p, because there's 5 of them. So this is specific to the cost in this situation, right? The algebraic expression that would describe this group's cost for any item in terms of the adult price and the child price. So if you notice, the first number, whether it was tickets, hot dogs, drinks, was just multiplied by 1. So that's just the price for 1 adult. And over here, they were all multiplied by 5. So the price, depending on what item you're talking about, the price of that item, which is the lowercase p, is being multiplied by 5 because there's 5 children. So regardless of tickets, hot dogs, drinks, this was what we plugged in for. Now, technically, there's a 1 in front of here, and so sometimes that's where students could get confused. They're like, well, where'd the 1 go? This is being multiplied by 1. Every coefficient, even up here, these x's have a 1 there. Every variable has a 1 as a coefficient. So we don't always write it, but it is there, so don't be confused. So this is 1 times the price of an adult item plus 5 times the price of a child's item. All right, number 9. Real quick, which expression has 3 terms? To have 3 terms, 3 separate products or individual numbers or variables being added together. So this is 1 term. They're all being multiplied. 1 term. This is 2 terms. 4ab is 1 term. 25 is 1 term. Separated by addition. It's 2 terms. So 2, 1. This is 3, and this is 1. So the answer here is just letter C. Okay, number 10. The following describes a pattern. A number is multiplied by 12. The product is then divided by 2. And then 3 is subtracted from the result. So give 3 instances of this pattern. So for part A, 3 instances, you're going to come up with any number. It says a number, so your instance can be anything. So I'm going to pick a number that I'm not using here so I don't get confused. So let's go with 5. and we'll call it x. X equals 5. So that number 5 is multiplied by 12, so times 12. The product, so the answer to this multiplication problem is divided by 2, and then 3 is subtracted from the result. Looks like that. So it wants 3 instances, so come up with another number. So let's go 10. Okay, so that number 10 is multiplied by 12. The product, the answer to the multiplication, is divided by 2, and that is then subtracted by 3. I'll move right next to it. 7 times 12 over 2 minus 3, just one more instance. Part B, now that you're looking at this, the 12 stays the same, the 2 stays the same, the 3 stays the same. What is interchanging? It is this number, so that's the variable. So when it says write the algebraic expression to describe the pattern if the original number is represented by n, so the original number, the one that's changing every single instance, that's n. So it's n times 12. Now we write that as 12n, but if you wrote it as n times 12 to match these others, that's not incorrect. But when we combine a variable and what becomes the coefficient, we put the number up front. So it's 12n over 2 minus 3. And we'll talk about later on in algebra that we would simplify this. The 12 over 2, that's division, it's actually 6. So this would become 6n minus 3. But for now, this is perfect. All right, and that was number 10. So we are on to number 12. So we're down here looking at the triangle. Use the following information. M is positive and n is greater than m. See, right away, I know people get lost in that right there. So that's kind of just high-level mathematical talk that has to be there when you fully understand this at the highest level to prove there are instances where this could be no good, like where you can't plug a 0 in here, right? So, or a negative number, because we can't have a negative length. So that's basically all it's saying. M and n is greater than this, blah, blah, blah. We can't end up here. So like, look, if m was bigger than n, we'd end up with a negative number because you'd have a small number minus a big number. But you can't have a negative length. So they're basically just saying, okay, we know it can't be 0, it can't be a negative number. So that's all they're going through there, blah, 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 blah. Just look at the picture. There exists a triangle with side lengths that are right here given to you. Answer the question. So a lot of people just get lost in all of this explanation up here. They're just going through stating the facts that we can't have negatives or 0 as a side length, basically. So just jump to letter A, use this diagram here. So n equals 2, this is A, and m equals 1. So find the lengths of the 3 sides of the right triangle. Okay, so we're just finding the actual lengths. It's pretty straightforward. So we have n squared plus m squared. So for that side length, you plug in 2 squared plus 1 squared. So that's 4 plus 1, so that's 5. I'm going to go right over next to it. 2nm, that's 2 times 1. Again, just plugging the numbers that they gave me directly in. So 2 times 2 is 4, times 1 is 4. So far I have a 5 and a 4. My other side length, n squared minus m squared, it's 2 squared minus 1 squared. So that's 4 minus 1, which is 3. So my 3 side lengths are 5, 4, and 3. Part B, same idea. Now n equals 3, m equals 2. I'm going in the same order. So n squared plus m squared. So 3 squared plus 2 squared, that's 9 plus 4. So I got 13. 2nm is 2 times 3 times 2. So that's 12. And n squared minus m squared. 3 squared minus 2 squared. So 9 minus 4, and I get 5. All right, turning the page, and we are jumping to number 14. So we're going to evaluate each expression, and then we're going to analyze kind of the pattern that's going on here. So starting with letter A, just evaluate means solve it. So 2/3 times 3 over 2. You could plug this in your calculator. We've practiced a little bit with how we do fractions in the calculator, but we should know straight across basic math here. 2 times 3 is 6, and 3 times 2 is 6, and 6 over 6 is 1. So what about the next one? 23 over 11 times 11 over 23. Now you could go ahead and plug that in your calculator and find out what it is. But when I do 23 times 11 and get that answer, and 11 times 23 and get that answer, they are going to be the same, are they not? So just like 6 over 6 simplified to 1, whatever this big number is, I'm going to get on the top and the bottom. This is just going to be 1. Negative 7 over 5 times 5 over negative 7. Easy enough numbers to run. Negative 35 on top, negative 35 on the bottom. Two negatives do make a positive, and this is positive 1. So you can see the very last one, 0.03 over 6. It doesn't matter if they throw a decimal at you. The product we get on the top is going to be the same as the product we get on the bottom. Same number over itself in a fraction form is just 1. So 14b. Describe this pattern. And then C, we're going to talk about, is it true for all numbers? So notice that whatever number is in this first spot also ends up here. So if you want to call that X, it doesn't tell you what letters to use, so we can use X times whatever this next fraction is. This number appears in both spots, and this number appears in both spots. A different number, so I'm going to put Y. You could use A and B. It's going to equal X times Y, and over here, Y times X, which is the same as X times Y, which equals 1. So that's the pattern. But then let's analyze it real quick. Do you think this is true for all numbers? At first you might say, yeah, we just did a bunch of these and every single one's the same. But, okay, we have some issues potentially if we plug in a 0. So if we put in a 0 over, let's say Y is just 5, it doesn't matter, and 5 over 0. First of all, we have issues with those numbers. We can't divide by 0. But if we went straight across, we'd end up with 0 over 0, which is 0, not 1, right? So that proves that this is not true for all. So it cannot equal 0. That would be the instance that does not let this work out. All right, we're going 15, 16, 17. So 15. So X is 58 and Y is 31. Evaluate this. So just plug in and solve. So kind of some big numbers. We'll use the calculator, but nothing here to be scared of. So both X values become 58 times the Y minus Y times the X of 58. Y is 31. And so regardless, if you want to run these numbers, fine, but you're going to get the same answer when you multiply 58 times 31 as you get when you multiply 31 times 58. So it's going to, when you subtract it from itself, the same number, you're going to get 0. Part B. Suppose the values of X and Y are changed. Will the answer to part A change? And your answer is no. Why or why not? So the book answer is the commutative property. And that was briefly talked about. Commutative property of multiplication and addition says if you switch the order of multiplication, you still get the same answer, which is why this will always hold true. Because, yeah, we can flip-flop the numbers here. We can put new numbers in if we want. But if we just change the order of multiplication of any two numbers, we're still going to get the same answer. And so when you subtract it, you're going to get 0. So this will always hold true because of that commutative property. (16). Okay, evaluating when X equals 2, Y equals 8, and Z equals 4. So plugging straight in. So X they said was 2, so 2 squared. And Y is 8, and that's not a 2, that's a Z. So Z plugs in and is 4. So 2 squared is 4. 8 over 4 is 2. Nope, I missed that. That was to the third power. Okay, 2 to the third power is not 4. 2 times 2 times 2. You can plug that right in your calculator. It is 8. So your final answer here is 10. And 17. Same idea, just a longer problem. So we need to stay organized here. and then follow our order of operations. So y is 8, z is 4, x is 2, z again is 4. So easy to put the wrong number in the wrong spot here. So going slow and being careful. 2 on the bottom. This is a z, which is 4. This is a z, which is 4 minus 1 to the 4th. All right. Once we carefully plug everything in, now it's just a matter of following in the order of operations. So this is going to be a 3. And we've got to take care of this as well. So 8 plus 4 plus. We end up with a 6 on top here. 4 times 3 raised to the 4th. So I took care of all the parentheses. This counts as parentheses. The top of a fraction or the bottom of a fraction counts as parentheses. So next is exponents. So 3 to the 4th, plug that in. It's 3 times 3 times 3 times 3, 4 times. That becomes 81. So this is 4 times 81. Next up would be multiplication and division. So what are we saving for last? We're saving the plus and the plus and the minus. So division has to happen, multiplication has to happen. So I'm saving this. 6 over 2 just becomes a 3. Minus, and I multiply, and this is 324. And now I go from left to right. Plus, plus, then minus, and you get negative 309 if you plug that all in correct in your calculator. All right, we are going to jump straight to the calculator here on number 20. Put this one in here for a reason so that we can find our pi button. Round pi to the nearest thousandth. So we want to find our pi button here, right here on these calculators. And you get 3.1415. Oops, 3.1415. You can go farther if you want to start with 92654. But we are rounding this to the nearest thousandth. The first spot after the decimal is tenths, then hundredths, then thousandths. So since they want us to round to the nearest thousandth, tenths, hundredths, thousandths, we're going to this spot. So everything before it's going to stay. We're just rounding the last number. So it's 3.14. And then this is my last spot. Basic rounding here. You either keep this number the same or you round it up based on the following number. 5 or higher on the following number rounds it up. So it becomes a 2, and this number is rounded to the nearest thousandth. And last one, some little basic pre-algebra practice here with some percentages, things we're going to need moving forward. 20% of a restaurant bill is left for a tip. If the bill is $34.76, what would be 20% tip rounded to the nearest dollar? So percentages, you can write as a decimal. So if you want to find 20% of something, you multiply by 0.20. So the decimal in 20 is after, just like every number where we don't actually have it written out. You move it 2 spots to the left. That's the same as dividing by 100 because a percentage is out of 100. So if you want 20% of something, you just multiply by 0.20. Hopefully you remember doing something like that in middle school. So all we have to do is 0.2 times $34.76. You get 6.952. And it's going to be rounded to the nearest dollar. So here's our dollar spot. More practice on rounding. This number either stays the same or goes up based on the next thing. So 95 cents or just the 9 itself rounds this 6 up to nearest dollar, $7. We're not given a tip with change. We're going to go up to the even dollar. So $6.95 rounds up to 7.